Good evening, welcome to this video for level 3 physics for level 3 waves, and we will be looking at interference. So in this video we'll be covering basic definitions for interference of waves, and we're going to be looking at Young's double slit experiment and diffraction gratings where we create the alternating patterns of bright dark fringes or alternating high intensity or low intensity sounds on a particular screen some distance away from the point sources. So I know I haven't uploaded a video in quite some time, so I do want to get back into uploading videos on a regular basis. So I will be doing some daily uploads, and I'll be doing weekly uploads as well. For the weekly uploads, I do want to focus on what I've been doing previously, which is my slideshows and doing some past NCA papers if that's applicable. But I also want to be starting to do some things I want to do called shorts, which is where I'm going to be doing some particular select questions that I find really interesting. For example, it could be any subject, it could be chemistry, it could be calculus, it could be physics. It's just some select questions, could be relevant, it could be scholarship or level just any question that I personally found and I found really enjoyable and very interesting. And I'll also be doing that on my channel, and I'll try to be uploading on a daily basis. So once again, it's good to be back, and I apologize that there hasn't been any videos in quite some time. Alright, so sorry for that, so just get back into the video. So we're looking at interference for level 3 physics. So let's start off with wave interference and what is wave interference. So wave interference is is occurring when two waves meeting across the same medium. So that's causing a net, we call combination of the two waves. So usually we will focus on two different types of interference. We're going to be looking at constructive interference. So this is when the waves arrive in phase with each other, and in phase means that the path difference between the waves is a whole integer wavelength. So basically it's n lambda, where n is always an integer, and the resultant wave produced is always a combined is also always a wave of combined amplitude of the individual waves. So the wave created will be one that has a bigger amplitude than both of the individual waves, and that's because they are arriving in phase. The second one is destructive interference, and this is when the waves are arriving out of phase, and this is where the path difference is half integer half wavelength. So that is, I was supposed to say n minus 1 half lambda, my apologies. So it's n minus 1 half lambdas, because when n is an integer, any integer minus 1 half will give us a half wavelength, which is going to be a point of destructive interference. And destructive interference is when the resultant wave is going to cancel out because it is the difference between the amplitudes of the two individual waves. So it's going to cause a wave with a smaller amplitude. And anything between half a lambda and lambda in terms of the path difference will have a combination of constructive and destructive interference. And then I have a image of constructive interference here. So we see that these two waves are in phase, and when the waves are in phase, they're going to combine to give waves with a larger amplitude. So in this case, since we have both of the same waves, we're going to have the amplitude is going to be two times the amplitude of the individual waves. And for destructive interference, it's going to be when the waves are exactly out of phase. So as you can see, for the first one, our peaks are in line with the peaks of the second wave, and the troughs are in line with the troughs, which is going to give us the constructive interference. But for our destructive interference, you see that the troughs for one of the waves is in line with the peaks for the other wave. So when they superimpose, we're going to be getting a destructive interference, because the path difference is a half wavelength. And that's going to give us, as you can see, since both of the waves have the same amplitude, they're going to cancel out completely, and there's going to be no waves observed in this case. Right, so we're going to look at the interference pattern created by two coherent sources. So interference pattern can be created using two coherent sources. Coherent sources are those that emit waves of the same frequency and consistent phase difference. So what this means when I say consistent phase difference is that they could be in phase or out of phase. But what I'm saying is just that when they are emitting waves, the phase difference is not changing, it's staying constant. So whatever it is at the start is always just going to continue to stay that way. So if it's out of phase at the start, it's going to be out of phase, or if it's in phase, it's going to be in phase. And the waves are always in the same frequency and will be in the same medium. So waves will interfere constructively and destructively at certain points, depending on what is the path difference at these points. So as we discussed earlier, we have constructive interference and destructive interference, and they occur at different points. Where we have constructive interference when the path difference is a whole wavelength, and destructive interference where it is a half wavelength. We know that constructive interference can always occurs across a common line, which is known as antinodal lines, and destructive interference occurs across common lines known as nodal lines. So antinodal lines is where we're going to be having constructive interference. So these are the places you're going to be observing the bright fringes if you're looking at light, and these are the lines you're going to be observing a loud sound if you're talking about sound waves. And the nodal lines is going to be when there's going to be cancelling out of the waves in terms of the amplitude, and you're going to get places where there's a dark fringe. So in this case, there will be a dark fringe, or there could be a quiet sound if you're talking about sound waves. So we should have covered this in last year in level 2. So we have our point sources, source 1 and source 2. We're going to be getting a interference pattern, and we're going to have different alternating antinodal and nodal lines. So the center line is what's called the central maxima, and on both sides of the central maxima, there are going to be antinodal lines and nodal lines, and it's going to be alternating. So there's going to be an antinodal line, and then a nodal line, and then antinodal line is going to alternate. And there should have been this question that last year that asked us that a person is walking from left to right, and then explain why that the person will be hearing alternating loud and quiet sounds. For example, if it's sound waves, and then you would be saying that there's going to be different antinodal lines and nodal lines, and they're going to be alternating as the person walks from, for example, point A to point B, because the path differences at these points are different. For example, some places it will be a whole wavelength, and some places it will just be half a wavelength. So it's going to create observations where there's going to be loud and quiet alternating sounds. So like I just said, so at an antinodal line, there's going to be a high intensity wave will be observed. So like I said before, this will be a very loud sound, or this could be a very bright fringe. And at a nodal line, a low intensity wave will be observed. So this would be a dark fringe if we're talking about light, or a very quiet sound if we're talking about sound. Right, so let's look at Young's double slit experiment. So Young's double slit experiment was done when monochromatic light, so that's just one color light, for example, like red light, blue light, green light. Okay, so that was shown through two parallel slits that were d distance apart. And since we know that diffraction occurs when the waves arrive at the slit, it's going to cause some interference pattern to be observed on a screen that's distance L away from the sources. So some observations that were made is that alternating bright and dark fringes appeared on screen. So that's similar to what we were talking before, how there's alternating antinodal and nodal lines causing alternating bright and dark fringes. And we know that the relative position of the dark and bright fringes changed with the wavelength of the light, and the central maxima always remained at the same position on the screen, assuming that the screen is the same distance L away from the sources, and we're just changing the wavelength of the light. So it could be red light, green light, because different colored lights have different wavelengths. The position of the dark and bright fringes were also affected by the distance that separated the slits. So that would be the distance d that's between the two parallel slits, and that also affected the relative position of the dark and bright fringes. And we'll be looking at these observations in greater detail. As a result, we came up with the following formula. So that's n lambda equals d sine theta for a bright fringe or for constructive interference. And also we have n lambda equals dx over L, which is also for constructive interference, because in this case, d sine theta and dx over L represents the path difference of the waves, and these are all equal to n lambda, which signifies that we are talking about constructive interference in this case. If we want to modify these formulas to talk about destructive interference, it's going to be n minus 1/2 times of wavelength, and that equals to the difference, which could be d sine theta or dx over L. So here's an example of a picture for Young's double slit experiments. We have two parallel slits and their distance d apart. I'm going to shine some monochromatic light through the slits, and what we're going to observe is that on the other side on the screen, we're going to be seeing that there's going to be alternating bright and dark fringes. So we're going to see that there's one bright fringe followed by one dark fringe to both of its sides, and then a bright fringe, and then dark, and then bright. It's going to be alternating. Alright, so let's talk a bit more about the formula that was derived. So if we look at two sources, we just call it P1 and P2, and we'll say that they're distance d apart, and we're going to say that they're some distance which is L away from the screen. So we're going to consider a point on the screen, and it's going to be a deflection of angle theta away from the central maxima. So let's just look at this diagram here. So we have our point 1 and our point 2. And our central line running through is just going to be the position of our central maxima. And I'm going to choose a point X, which is say it's X meters away from the central maxima. And that is also angle theta away from the central maxima. So that's going to be where our point X is located. And basically, we're going to be what we're trying to do here is trying to find the path difference of P1 and P2 at this particular point. We're going to call it point X. So in this case, we can see that P2x is obviously longer than P1x. So therefore, there's going to be a path difference since the distance it takes for the light to go from point source 2 to x, it is longer than the distance taken for the light to go from point 1 to x. So therefore, there's going to be a path difference. And that path difference we're going to try to find. Okay. So what we can do here is that we can draw a line from P1 onto the path of P2 to x. And we're going to draw this line so that QX, so the length of QX is equal to, okay. So the length of QX is equal to the length of P1x. So we're just going to draw it such that that is true. So that's QX equals to P1x. So therefore, the path difference of P1 and P2 to x will just simply be QP2, the distance of QP2, which we're going to be trying to find. So if we do some angle geometry, so we can see that the angle P2, P1Q, the angle made between those lines is going to also be theta. And therefore, we can say that by using our trig formula, we can say that the path difference, so basically we have sine theta is equal to our path difference, we'll call it P for now, divided by the distance between the slits. And if we rearrange to make P the subject, we're going to get that the path difference is equal to d sine theta. So in this case, we have our path, that's our path difference. D sine theta would be our path difference. And if we want constructive interference to occur at point X, D sine theta must be equal to a whole number of wavelengths, which in this case, we can just say is n lambda, where n is an integer. So therefore, the formula that n lambda equals to D sine theta is created. If we want X to be a point of destructive interference, so for example, this might be a dark fringe, we're definitely going to have to say that the path difference will be a half a wavelength. So that would be n minus 1/2 lambda equals to the path difference, which is d sine theta. Right, so that's where the formula comes from. And the second formula is n lambda equals dx over L. So we're going to go back to the same image we just had before. So in this case, we're going to make an assumption that tan theta is equal to sine theta for very small angles. So that's going to occur when tan theta is when theta is very small, then tan theta is approximately equal to sine theta, which can be a decent approximation for small angles, basically. So in this case, we're going to go back to what we had before. So sine theta was equal to our path difference, which is QP2, divided by the distance between the slit, which is d. That's our sine theta. And this time, we also can say that tan theta is equal to x over L. Because if we have our angle theta here, the distance x is basically the distance from the central maxima. So that's just the distance from the central maxima to our point x. That's our distance x. And we have tan theta equals to x over L, because if you look at the triangle that is formed between our central maxima and the line that deviates from the central maxima to x, that creates angle theta. And we can say that tan theta equals to opposite over adjacent, which in this case would be the distance x from the central maxima divided by the distance between the the screen and the sources, which in this case we're going to call it L. So therefore, tan theta equals to x over L, and we know that sine theta equals to path difference over our distance between the slits. So we know if we make sine theta equals to tan theta, we can see that dx over L equals to n lambda for constructive interference, because like I said before, constructive interference is when the path difference is a whole integer wavelength, so that's n lambda. And if you want it to be for destructive interference, you're going to have to use n minus 1/2, because we want a half wavelength times the wavelength for destructive, so it's half wavelength path difference. and that equals to dx over L. So that's where both of the formula comes from. I hope that makes some sense. So, okay, so if we want to use n lambda equals dx over L, so here's an example question. We have Jonathan is shining a green laser. Its wavelength is 550 nanometers. Nanometers, that's 1 times 10 to the power negative 9 meters. So in this case, it will be 550 times 10 to the power negative 9 meters. And he's going to shine it for a double slit, and the spacing is 0.04 millimeters. And remember that 0.04 millimeters, so 1 millimeter equals to 0.1 centimeters, and 1 centimeter equals to 0.001 meters. So 1 millimeter equals 0.0001 meters. Okay, just remember your conversions, just be careful. So given that the screen is 40 meters away from the slits, calculate the distance that the second order fringe, so that's referring to the second bright fringe, so you know how we're going to have our central maxima. And our first order fringe is the first fringe from that central maxima, and our second order fringe will be the second bright fringe from the central maxima. So just want to calculate the distance from the second order fringe or from the central maxima. So in this case, I'll just have a demonstration of what it will look like. So we're going to have our second order fringe a distance x away from our central maxima, and that's going to be a distance L away from our point sources, and that's going to cause a deflection, which is, we'll call it angle theta. Okay, since we know that L is a lot greater than D, so L is, we can see it's 40 meters, and we see that our distance between the slits is 0.04 millimeters. This is quite a significant difference because 40 meters is far greater than 0.04 millimeters. So therefore, we can say that the angle theta is going to be very, very small. Therefore, our approximation made to derive the formula, so we had our tan theta equals to sine theta. That's the assumption we made. So we make that assumption, so that assumption is going to be held pretty accurately for these small angles. Therefore, we can use the formula n lambda equals dx over L. So in this case, we have our wavelength, which is 550 times 10 to the power negative 9 times 2. Because the reason we're timesing by 2 is because n is always the order fringe that is away from the central maxima. So for example, the first order would be n equals to 1, second order would be n equals to 2, etc. So third order, third bright fringe on both sides would be n equals to 3, and then etc. So then we have 2 times 550 times 10 to the power negative 9. That's our n lambda. And that's equal to our distance between the slits, which is if we convert 0.04 millimeters to meters, we'll get 0.00004 meters, times the distance x, that is between the second order fringe and the central maxima, and that's divided by the length, which is 40. If we rearrange to find the distance x, we will find that the distance from the central maxima to the second order fringe is about 1.1 meters. Alright, so here's the calculation for another one using n lambda equals to d sine theta. So we look at this example. So we have red light is shown through a double slit, which is distance is 0.01 millimeters apart. The light has a wavelength of 700 nanometers. So there's 4 parts here, so you can just read the parts and try to do the question yourself first. Right, so question A, we have calculate the angle that the line makes the line makes with the central line. So we're talking about sorry, I should be more clear. So we're talking about the first order line. So for the first order line, we know that n lambda equals d sine theta, and we know that for the first order line, n is going to be equal to 1. So in this case, if we basically for these questions, it's basically just using your numbers and just putting into the formula. So we can find that theta equals to 4.01 degrees. Remember, your calculator should be on degrees, not radians. And in this question, when you're trying to find out the angle theta, you're going to move everything to one side. So you're going to make sine theta equals to some number. And then you're going to take the inverse sine of both sides. So sine inverse of that particular number, and you're going to get the degrees. Sorry. So in this question, you should have got the first order fringe is the deflection 4.01 degrees from the central maxima. Looking at question B, so we want to calculate the angle for the third bright fringe. So the third bright fringe is going to be n equals to 3. So it's going to be the exact same process, except our n equals to 3. At this time, you should see that theta equals to 12.1 degrees. Question C, calculate the angle for the first dark fringe. So this time you should be using I should say n minus 1/2 lambda equals d sine theta. So in this case, we have n minus 1/2 lambda equals d sine theta. So therefore, for our first dark fringe, it's going to be when our n equals to 1, but we have to subtract 1/2 because we want the path difference to be half a wavelength. So in this case, since it's a multiple of half a wavelength, we're going to see some destructive interference occur, and therefore we're going to see this is going to be a dark fringe. So that's going to be where the first dark fringe is observed. And so if we substitute those numbers in, we'll find that theta equals 2 degrees. And you should always check if your answer makes sense. We know that the central maxima is a place where it's a bright fringe. And like I said before, it's always going to be alternating bright and dark fringes. So we know that after the central maxima on both sides, we should see a dark fringe before we see a bright fringe because it's alternating, right? So our answer of 2 degrees, which is less than our first order bright fringe, means occurs sooner than our first order bright fringe. That answer makes sense because we know that the dark fringe will occur before the bright fringe. So question D, we're trying to find the total number of bright fringes observed. So the angle deflection for any particular bright fringe cannot exceed 90 degrees because if it exceeds 90 degrees, if it's exactly 90 degrees, then the light's going to go perpendicular to the sources and it will actually never reach the screen if you think about it. Because if it's 90 degrees, then it will never ever reach the screen and therefore it will not be observed on the screen. So therefore the maximum number of fringes observed from the screen is only for when the angle of deflection is less than 90 degrees. So basically our maximum angle is our very, very maximum is 90. So therefore we're going to substitute theta equals to 90 and we're going to find the n value. Once we get the n value, we're going to have to round it down to the nearest lowest integer number to find the number of the highest order line that can be observed. So in this case, we can just substitute our numbers in, except this time we don't know what n is, and we're going to substitute theta equals to 90. If we make n the subject, we'll find that n equals to 14.29. So what does n equals 14.29, what is this representing? Is that there are 14 bright fringes on each side of the central maxima. So 14 bright fringes on each side of the central maxima. So we have two sides for the central maxima. So we're going to have 14 to one side and then 14 to the other side. So that's already 28 bright spots. And if you include the central maxima itself as a bright spot, we're going to be observing 29 bright spots, okay? In this question, we'll be observing 29. And we'll always round it down to the nearest lowest integer numbers because our highest order that can be shown on the screen is 14. So therefore our 14th one is the highest, therefore there's only 14 from on each side of the central maxima. It's not 15 because the 15 one is actually not visible because the angle theta is more than 90 degrees, and we know that if it's more than 90 degrees, it's actually never going to reach the screen, therefore it's not going to appear on the screen. So therefore only 14 bright fringes will appear on each side of the central maxima. And if you want to count the total number of bright spots, you can just use 2n plus 1. So total is just 14 times 2 plus 1. And that logic once again being that there's equal number of bright fringes on both sides of the central maxima. That's going to give you 2 times of your n. And if we want to include the central maxima itself as a bright fringe, you're going to have to add another 1 for that central maxima. So in this case, we would say that there's 29 bright spots. So total number of bright fringes will be 29 bright fringes. Alright, so we're going to look at what's going to happen if we change the wavelength. So changing the wavelength of the light changes the position of the fringes in the screen. Waves of different wavelength will interfere constructively and destructively at different angles. As the wavelength increases, the angles of constructive and destructive interference increases. So as we increase the wavelength, the angles of constructive interference and destructive interference are going to increase. Therefore, a particular order fringe will be further away from the central maxima than for a lower wavelength source. Okay. So if we apply this knowledge by shining a white light through a double slit, so we know that white light is made of a whole spectrum of colors. So, you know, like your spectrum, like your red, your violet, your green, your blue, etc. So made a whole spectrum of colors. And each of these colors will have a unique wavelength. So for example, red has a different wavelength to green. The green has a different wavelength to the violet. And the violet has a different wavelength to the orange, okay? So each wavelength will interfere constructively and destructively at different angles. So for example, red has the highest wavelength and therefore will interfere at the largest angle. Therefore, constructive interference will occur at the largest angle. Therefore, a particular bright fringe for red is going to be located further away from the central maxima than for a lower wavelength light, for example, violet. That's because violet has the lowest wavelength. Therefore, its position of constructive interference is going to occur at lower angles from the central maxima. Therefore, it's going for any particular fringe, the violet light will be located closer to the central maxima than the red light. So therefore, if you're observing your spectrum, you should see that it's the violet that comes first and then the red that comes at the end of each particular spectrum of colors. So if we look here, as you can see, our central maxima is white, and I'll explain why it's white just in a moment. But if you look at both sides of the central maxima, you'll see that the violet light will appear first. That's because violet light has the lowest wavelength and it's going to have constructive and destructive interference at a smaller angle from the central maxima, while red will have constructive and destructive interference at a larger angle, therefore it will be further away from the central maxima. The reason that the central maxima is white is because at the central maxima, all of the color lights will recombine to form back to our white spectrum. Okay, so it's gonna be at the different orders. There's gonna be they're going to interfere at different angles, causing the spectrum. But for the particular case where at the central maxima, the angle theta is equal to 0 because it's at the central maximum line. So therefore, all of the light is just going to remain. All the light is just remaining. So therefore, it's just going to be a recombination of all of the colors, which is going to form your white light at the central maxima. Alright, so now we're going to look at diffraction gratings. So diffraction gratings and double slit is slightly different because a double slit will only contain 2 slits, but the diffraction grating will contain many slits, which is usually specified, okay? But it's going to be a lot more than just 2 slits. So therefore, there's going to be more points of interference because there are more points, more slits for the light to interfere. So the distance between the slits are also smaller for the diffraction grating because there's a lot more slits. So therefore, by logic, your distance between those slits are obviously going to be smaller. Yeah, so the distance between adjacent antinodes are smaller. So there are more points of constructive interference and destructive interference because there's more point sources. If there's more point sources and there's going to be more points of interference, which is more available positions of where your constructive interference can occur and your destructive interference occur. Therefore, your bright fringe is going to be sharper because there's more constructive interference at when the wavelength is equal to a whole wavelength. While the dark fringes can almost have complete darkness because when the when the path difference is half a wavelength, that's going to have it's going to be more areas where all the light can cancel out. Therefore, there's going to be pretty dark places, pretty dark areas between the 2 bright fringes. So if we just draw a table here to compare the two different types of. For double slit, we see that the similarities between double slit and diffraction grating is both will be involving interference, so constructive interference and destructive interference, okay? And both can use the same formula, but the difference is that the double slit has less points of CI, therefore the fringes are less well defined, and we know that diffraction grating will have its fringes closer to each other due to smaller separation. That's because of d sine theta. So d sine theta equals to n lambda. So therefore, d is proportional to sine theta. Therefore, as the distance between the slits decrease, the theta deflection from the central line will also decrease. Therefore, the fringes will also be closer to each other. All right. So lines in the diffraction grating. So sometimes the distance between slits is not stated in the question for diffraction grating, but it's given as a measurement usually as x number of lines per unit of measurement. So for example, you might expect the question to say, oh, the distance between the slits is, for example, 3 millimeters. But usually they will give it as, oh, there are 100 lines per centimeter. And simply what this means is that there are 100 of slits per centimeter, and you have to use a formula to find the distances between those slits. So in order to do that, we can use the formula d equals to 1 over n. And d is the distance between the slits in meters, that's what we're trying to find. And n is the number of lines per meter. Okay, that's very important because our distance is measured in meters. Therefore, our number of lines must be in per meters as well, or else our units are not going to be completely correct, and we're going to get the incorrect value for d. For example, if we look back to our example, which is 100 lines per centimeter, if there's 100 lines in 1 centimeter, then there's going to be 200 lines in 2 centimeters and 300 lines in 3 centimeters, etc., right? So therefore, since there's 100 centimeters in a meter, It's going to be 100 times 100, which is 10,000 lines in a meter. Therefore, our distance between the slits will be 1 over 10,000, which in this case will be 0.0001 meters. Alright, so some questions involving diffraction gratings. So for this question, we have Samuel shines a red light, which is say the wavelength is 700 nanometers, and a violet light, so we say that that wavelength is 350 nanometers. Through a diffraction slit diffraction grating of 300 lines per millimeter. So I'm going to give you, so you can read the question. I'll give you some time to try to figure out the answer, and then I'll walk you through how we can approach this question. Right, so question A, so find the angle to the central maxima for the first order fringe for the red and violet light. So that's pretty straightforward question. We can just use our n lambda equals to d sine theta for both cases. So case 1, which is with the red light, and case 2 is with the violet light. So first things first, we don't know what our d is just yet. We need to use our 300 lines per millimeter to find the distance d. As we established above, n is the number of lines per meter, not the number of lines per millimeter. And we know that there's 1,000 millimeters in 1 meter, so therefore we have to multiply the number of lines by 1,000. So 300 will become 300,000 lines per meter. So therefore we can say that d equals to 1 over n. 1 over 300,000 will give us d equals to 3.333 times 10 to the power of negative 6 meters. So now we can use our n lambda equals d sine theta to find the first order fringes for the red and violet light. So for red, n lambda equals d sine theta, and for the first order fringe, our n is simply equal to 1. So if we plug in our numbers there, we make sine theta the subject, and we take the inverse of both sides, we should find that theta equals to 12.1 degrees. Looking at the violet light, we have n lambda equals to d sine theta as well. And we know that n equals to 1, and our lambda equals to 350 nanometers. So we know that wavelength is 350 nanometers. So therefore, if we make sine theta the subject, and we take the inverse of both sides, we'll get theta equals to 6.03 degrees. All right, looking at part number B. So that's the maximum number of fringes observed for both the red and the violet light. So once again, we established above that the maximum angle deviation from the central line is 90 degrees. So we're going to follow the same process to find our maximum number of fringes observed, the bright fringes observed on both sides of the central maxima. For red, we have n lambda equals to d sine theta. And if we substitute our values and theta equals to 90, we'll find that n equals to 4.76, which is corresponding to 4 red fringes on each side of the central maxima. So in this case, if we shone red light through the diffraction grating, we'll see that there's going to be 4 red fringes on the left and 4 red fringes on the right, and it's going to be a bright red spot at the center, which is the central maxima. Therefore, 4 plus 4 plus 1, that's going to give us 9 total bright areas for the red light. For the violet light, we're going to follow the exact same process, except we're going to change the wavelength to 350 nanometers instead. So if we plug our numbers in, we should get n equals to 9.52. And this corresponds to 9 violet fringes on each side of the central maxima. So once again, it's going to be 9 on the left, 9 on the right, and it's going to be a violet fringe right down the middle. So therefore, the total number of bright violet fringes will be 9 times 2 plus 1. That's going to give us simply 19 violet fringes. Alright, so question C. Okay, so question C. So red fringe will arrive at the same position as the violet fringe. That's going to occur when the angle deviation is equal. So that's when the angle of the red is equal to angle of the purple light. So in this case, we're going to write out our n lambda equals d sine theta for both. So we have red. So in this case, we don't know the particular order that they will overlap, and we don't know when this will happen in a particular angle. But all we know is that the angle is the same because they're at the same position. Therefore, on the same position on the screen, that means that the angle theta deflection must also be the same. So we know that theta is equal to the theta red equals theta violet. So if we look at our violet one, we have our, we write out the exact same thing, except our n1 and n2 is different, but we have our same sine theta. If we divide red by purple, so we just take the two equations and we say it's just put the red formula divided by the purple formula, we'll see that what we'll get is pretty telling. So if we have 700 nanometers divided by 350 nanometers, that's going to give us 2. So therefore, we see that if we divide through, because the right hand side is the same, so we have our d sine theta, that's exactly the same because our bright fringe occurs at the same position. We're going to see that 2n1 equals to n2. And what this means is that every second purple fringe will overlap with the first red fringe. So when the first red fringe is when n1 equals to 1, and the second purple fringe, which is n equals to 2 for purple, is going to overlap with n equals to 1 for red. Similarly, if we have n1 equals to 2 for red, so red 1 is the second order, then our fourth order purple fringe is going to overlap with that red 1, and then it will be 3 and 6, and then 4 and 8, and that will be the last one. 4 and 8 will be the last overlap, and the reason for that is because we established there's only 4 red fringes on each side of the central maxima, and only 9 violet fringes. So the fifth overlap will not occur on the screen. Alright, so thank you for watching this video. I hope you enjoyed, and I hope to see you all in the next one. Thank you. Bye.